So in this lesson, we're going to be talking about independent versus dependent probability, and we're going to learn how to calculate dependent probability. So we're going to go ahead and figure out what would you do and why this is important. So what would you do if you were on a game show and you had a chance to win some money? And here's how it goes. You're offered the chance to win $5,000 cash, and the host points to 3 doors on the stage and says, behind each door are 2 boxes, but only one box behind only one door has the cash prize. So which door do you choose? The blue, the red, or the yellow? And is the probability of winning equal for any door? So which one would you pick? So let's think about this. There's how many boxes altogether? If there's 2 boxes behind every door, there has to be 6 boxes. And only 1 out of the 6 is the winning box. So if you chose this door here, that means your probability of choosing that door was 1 out of 3. And then there was 2 boxes. So that means in order to get to this box, we'll say the blue box 1. So we'll call it blue 1 versus blue 2. That means the probability of getting to that one is 1 out of 6, right? And so this box, these boxes here, this would be red 1 and red 2, and the probability of getting those is 1 out of 6 and 1 out of 6. So I would say that the probability of getting to each box is the same. But as soon as you pick, is the probability the same anymore? Because once you've gone ahead and you've chosen one door, now what's happened? Well, what if the prize had been behind the red door? What is your probability now that you are going to win? Well, would it have changed? Things to ponder. So this is a case of what we call dependent probability, because the outcome depends on the first thing that you did, which was make your first choice. So there used to be a game show on TV, and the host used to go ahead and have a little game at the end that was kind of like this. And they always used to make you some offers at the end. So the host makes you an offer at the end, and it's like, okay, well, you've already won $1,000 on your show today. Now, to help you increase your chances, if you agree to give up $500 of your winnings right now, we'll eliminate one of the doors that definitely does not hide the winning box. Should you take the deal? Now, remember that blue door? We said, okay, well, what if that blue door definitely did not have a winning box behind it? Because now, remember, your chances of just randomly getting the box was 1 out of 6, no matter which door you chose. But now, if you've eliminated it, now there's red 1, red 2, and there's yellow 1 and yellow 2. So there's only 4 boxes. So what's the probability now of you randomly choosing one of those correct boxes would be 1 out of 4. So have you increased your chances? Yeah, the probability of picking from 6 versus from 4 is obviously a better deal. Now, of course, if you chose the red door and the winning prize is behind the yellow door, have you really increased your chances? Well, no, but that's why it's all chance. Okay. So what we're going to do today is we're going to not figure out this game, because this actually is called, I believe, the Monty Hall game. And we're not going to figure that out today, but I will go ahead and I will leave you a clip later on where you can figure it out. Okay, so what our job today is figure out independent versus dependent probability and what it means. Okay, so what we've been working on so far for probability is independent. It's 2 or more events whose outcomes don't change based on the outcome of the other event. Okay, so what does that mean? Well, some things like rolling dice. If you roll a dice, there's 6 sides. Okay, so just like this one. And if I roll the first dice, it's always going to have 6 sides. So I have the possibilities of getting a 1, 2, 3, 4, 5, or a 6. And if I roll the dice a second time, I'm still going to have those same possibilities. So nothing is going to change. Okay, so that's what we call independent events. Anytime I go ahead and I do something that's not going to change what's the outcome of the second event, then they are considered to be independent. Okay, now sometimes we might be asked to spin a spinner. Well, a spinner is always going to have independence no matter how many times we spin it, because the outcomes are always going to change because we're not going to be changing the spinner theoretically. Okay, when it comes to things like cards or picking from a jar, like the marbles here, okay, they're only independent if we have replacement. That means you pick it and you put it back. Okay, so before you pick a second card, you have to put the first card back. Before you choose the second marble, you have to put the first one back. That's what keeps them independent. Okay, dependent events, on the other hand, is when you have 2 or more events, but the outcomes of the second and subsequent events change based on the prior event. So again, okay, things that are independent, like rolling a dice, are always going to be independent. But things like choosing a card, okay, without, that's my abbreviation for without, replacement, are always going to be dependent. Why? Because as soon as you choose one, you have less cards in the deck. So you have less things to choose from. So choosing anything from a group, okay, without replacement is always going to be dependent events. So if you were in a class and your teacher randomly calls on a student's name, but has a rule that they're never going to call on the same student twice in one class, and your name just got chosen, then you can be happy that you're not going to be called again. Okay, so let's go ahead and calculate dependent probabilities. So if we were asked to figure out what's the probability of drawing 2 aces in a row from a deck of cards, well, first we got to remember there's 52 cards in a deck, and 4 are aces. So let's go ahead and think about the first card. Okay, so for the first time we choose a card, we have 4 aces in the deck out of 52 cards. The second time that we go ahead and we choose the card, so now we're going to go ahead and make our second choice. We have 51 cards, because remember we've already picked one. And had that first card been an ace, how many cards left are ace? 3. So the reason we're doing 3 is because there's 3 aces left. And the reason we have 21 is because we did not replace. Okay, so we have already gone ahead and withdrawn 1 card. 1 less in deck. Okay, now what do we do to calculate our probability? We multiply these together. So we go ahead and 4 times 3 would be 12. And 52 times 51. So 4 times 3 would give me 12, and 52 times 51 would give me 2,652. And if I go ahead and I reduce that, I end up with 1 over 221. So the probability of getting 2 aces in a row is a lot lower than getting just 1 ace in a row, or 1 ace from the deck. Okay, so here we have Doug the dog. Okay, we want to know what's the probability that Doug the dog is randomly going to steal 2 bones in a row from these items. Okay, so we have to figure out what he has to choose from. So he has 1, 2, 3, 4, 5, 6, 7 items to choose from. So the first pick, he has 7 items to choose from. And how many of them are actually bones? Well, there's 1 bone, 2 bones, 3 bones. So he has 3 bones that he can choose from. And the second time he picks, because he picked 1 bone the first time, now he only has 6 things to choose from. And if his second pick is a bone, he only has 2 bones left to choose from. Now, when we're going ahead and we're actually doing this multiplication, we can reduce in the problem. So if I go ahead and do 3 goes into 3 once, 3 goes into 6 twice, 2 goes into 2, and now I have 1 times 1 and 7 times 1. That's a pretty good probability. And Doug, here he is, so cute, would probably do it. He loves bones. Okay, and that's the basics of calculating dependent probabilities.